Now that we've talked about those p-values, you might want to know, how do we get a p-value? How do the statisticians that work on all these studies calculate those numbers that they're going to put into the papers that you're going to read? So we're going to talk today about hypothesis testing. We're going to show you briefly how we choose which statistical test to use and give you some examples, and we're really going to avoid all the math. The purpose of this course is not to teach you how to be a biostatistician, but so that when you see those words written in an article, you'll know exactly what was going on. Now, the choice of a statistical test reminds me of kind of using the right tool for the right job. You have to, each statistical test is a tool, you got to kind of match it to the job it's doing. I had a bit of an interesting experience with this last weekend when I was building a wooden leprechaun box with my daughter for a school project. All right, so the basic idea is that we're going to put these wires through the side here to represent sort of the bars of the leprechaun cage, but in order to hold the wires, we're going to put these little tacks in. So I'll do the first one, and you'll do the rest after that. So basically, like this, like, ow. Sorry. Ow. Yeah.
Dad.
Yeah.
It's not going to work.
Yeah, I can't find my hammer.
Can you use your eyes and look around?
Okay, all right. That's nice. We didn't do so well on that. In any case, let's go back to that concept of difference. You remember in the last lecture when I was talking to you about the internal medicine docs and the surgeons and how I was going to measure their weights, and we could assign a p-value to the difference and see how weird our results would be assuming that they just are the same weight. So just to remind you, we were asking, are surgeons heavier than internal medicine doctors? And we measured a sample of them, and we found that the average internal medicine doc weighs 175 pounds and the average surgeon weighs 180 pounds. And then we asked this question, right? Is 175 different than 180? And of course, you're all saying yes, right? Because 175 does not equal 180. But in the world of statistics, you'll see people using this language all the time. They'll say, oh, are those two different? They don't mean, are they literally different? Of course they're different. What they mean is, are they statistically different? Are they distinguishable using mathematics? And so oftentimes people will say, oh no, those aren't different, even though the numbers themselves are different. They're talking about statistics. Now, calculating those p-values from coin flips is pretty easy, right? Remember, getting one head in a row, assuming you had a regular old-fashioned coin, would be a chance of 50%, and more heads in a row, the level kind of goes down by a stepwise fashion. But medicine isn't coin flips, right? Most of our data is not someone flipping a coin. The measurement of weight in our doctors, for instance, isn't similar to a coin flip. So the specific equations to calculate p-values are beyond the scope of this course, but you just need to know how a test gets chosen. And the good news here is that you really only need a couple pieces of information to choose which statistical test, or to recognize if the right statistical test was being used in a given study. You need to know what type of data is my exposure. So remember back to our talk about types of data. And you need to know what type of data is your outcome. So we've talked before about linking exposures to outcome. We just need to add that layer of what type of data is my exposure and outcome. So here is the master chart, okay? So what I've done here is I've listed the types of exposure, types of data you can have for an exposure and the types of data you can have for an outcome, and listed a statistical test. And I'm going to give you some specific examples of all of these. But just to show you how to read this table, if your exposure is a categorical variable, like let's say gender, and your outcome is a categorical variable like death, you would compare those with a specific statistical test, a specific tool. In this case, it would be called the chi-squared test or the Fisher's exact test. And those of you who had some statistics in college might remember those tests. The rest of you, I just don't want you to be afraid if you read these in a medical paper and it says, oh, we used the chi-square test to evaluate this. All they are is saying, this is the tool we use to generate that p-value we're reporting to you. Okay, so it tells you something about the type of data. And you can see if the exposure is continuous and normally distributed and the outcome is categorical, you would use something called the student's t-test. I'm not going to walk through each one of these. We'll reproduce these for you. And this is something you can always look back at. I also want to note that this assumes generally that we're comparing one thing to another thing. There are special tests that you can use when you have multiple groups. So instead of like men versus women, if you had multiple racial groups, for example, there's a kind of special set of tests there. And this doesn't talk at all about multivariable testing. And so we'll get later in the course to the idea that instead of just comparing, age to death rate or something like that, you might want to adjust for other variables like smoking status or income or something. And so you're putting more variables into these equations. That's its own thing. Right now, for this type of statistical testing, we're just comparing one thing to another thing. So let's go through some examples, and I think you'll get a feel for it. So here's a really encouraging article I recently read about a condition called Hutchinson-Gilford progeria. This is a genetic syndrome of rapid aging, and so these kids they start aging very rapidly, they lose their hair, they have very low muscle tone. The natural history of the disease, unfortunately, is that these children tend to die somewhere in their teen years. So there was a new drug that they were trying for this, a drug called lonafarnib. I won't go into the mechanism. And they did a small study. You can see the numbers of patients here. And they gave some of the kids got lonafarnib and some did not take the drug. And then we look at the number that survived and the number that died. Okay, and so what you can see here is that in the lonafarnib group, 59 kids survived and 4 died, compared to 46 survivors and 17 deaths in the nothing group. So I just want you to feel in your heart how weird that data is, assuming that lonafarnib does nothing. Does that data feel weird, assuming the null hypothesis? It does to me, and it should to you too. This is a little weird. It intuitively feels weird. And if we put this into a chi-square test, because that chart tells us to put it into a chi-square test, we could put these numbers in and we'd get a p-value of 0.002. So results this weird would only happen 0.2% of the time, assuming that drug doesn't work. So that is encouraging evidence that this drug might work. Remember, this p-value just tells you how weird it is assuming the drug doesn't work, but very encouraging study here. All right, let's talk about a continuous variable across groups. So this was an article looking at a drug called flibanserin, or it's being marketed as Addy, for hypoactive sexual desire disorder in women. So this is sort of a libido-enhancing drug. And the metric that they looked at in the two groups, so one group of women got placebo and one group got this drug, and they looked at this metric called the change in the number of sexually satisfying events per month. And so they had women report how many sexually satisfying events they had over the course of a month. And what you see here is that that number increased in the placebo group by 1.1. So there's some placebo effect here. Even the women on placebo had about 1 extra sexually satisfying event per month. And, but it went up by 1.9, almost 2 sexually satisfying events per month in the flibanserin group. And you can see the distribution of the results here. So the placebo group is in blue. Everyone is kind of shifted above 0 because most people did better. Some people had fewer sexually satisfying events per month. And then you can see people coming all the way up. Some people had even 10 extra sexually satisfying events per month. Very encouraging results. Of course, we see that in the placebo too. So you can tell with this continuous data, when we're comparing it, it's harder to intuit how weird this is. I don't have a good intuition just looking at the picture to say, oh, how much better is this? I can't assign a p-value quite as easily using my head, but we can use students' t-test to go ahead and give us a p-value. And in this case, the p-value was reported as less than 0.01, so about 1%. You'd get data this weird 1% of the time, assuming this drug does nothing at all. That's suggestive that the drug has some effect. All right, what about correlations? So this was an interesting study looking at doctors by specialty. And what it looked at was how empathetic they were on the y-axis here. So higher is more empathetic, more caring. and how Republican they are is on the x-axis here. And so what you can see are these dots are the various specialties, and there seems to be a correlation, right? The more empathetic a specialty is, the less Republican they are, and sort of vice versa. There's that kind of negative correlation. And we can use a Pearson's correlation test, that's the proper tool for this job, to generate a p-value associated with this correlation. And this I do think you can kind of eyeball and say, you know, this seems like there's something here. This data, assuming there's no relationship between empathy and republicanism at all, this data would be pretty weird, right? And indeed it is. Again, the p-value was reported as less than 1%, less than 0.01. It turns out psychiatrists are the most empathetic of the specialties and the most liberal, which makes a lot of sense. I know some psychiatrists. And those surgeons and anesthesiologists are on the other end in terms of empathy and liberalism. So what I've done during this brief talk is just to show you that statistical tests are all about asking how different two samples are and trying to quantify that in some way. Now, we are never 100% sure that they are different in that statistical sense, but we can describe how weird the results are, assuming they really aren't different. Again, that's the concept of the p-value. The correct statistical test is just dictated by the type of data present. So all you have to decide is what kind of data you have, and then you can just plug your data into a statistical test calculator and get a p-value. So now you know how those p-values come about. I'll see you next time.